This guy here is a Kangal. He's the national dog of Turkey and has been working alongside us human beings to guard flocks of sheep and cattle since the 12th century. He also has the strongest bite strength of any dog breed known, at 740 pounds per square inch, way more than 3 times the bite strength of a pit bull, that dog known for its powerful bite, which makes me think that pit bull's reputation is a touch overblown. But in any case, you don't want to steal a sheep when one of these is watching, considering it takes about 520 pounds to crack a human skull. If I owned one of these, I'd name it Venus. If I owned a second one, I'd also name it Venus. And if they bit you at the same time, it would hurt just as bad as walking around on Venus, provided you also inhaled a cloud of acid and then burst into flames. And yet, even with the bone-crunching potential that just the air has on Venus, out of all the other planets, moons, and asteroids that orbit our sun, Venus offers us the best chance for terraforming a new Earth. Maybe the only chance. This video is the second in a 2-part series. If you haven't seen part 1, it'll explain what terraforming is, how we might do it, and why Mars is a sucker's pick for the process. Just pause this video and click the little letter I way up in the corner over there, then come back and watch. We'll wait. Sweet. Let's talk about Venus. The planet, not my dogs. Venus is our closest neighbor in the solar system. Its gravity is more than 90% of Earth's, and unlike Mars, it has an atmosphere. Mars lost its atmosphere due to the failure of its magnetic field. Venus has more of a magnetic field than Mars does, but it doesn't actually make all that big of a difference. You see, Venus is 95 million kilometers closer to the Sun than Mars is, which means it gets about 240 times the solar energy blasted into it. Which means its adorable little magnetic field makes about the same difference as skydiving with an umbrella, as far as the end result is concerned. But Venus still maintains an atmosphere, and not just any atmosphere. The air on Venus is composed of 96% CO2, and has an atmospheric pressure more than 90 times that of Earth's. Venus's atmosphere is so thick that all the solar particles crashing into it make very little difference to its overall composition. To give you a sense of context, in 1963, the United States lost the submarine USS Thresher when it suffered equipment failure near its max test depth. As it sank, sonic sensors recorded the implosion of the hull at a depth of around 730 meters. The water pressure at that depth was so great that the hull of the ship failed, and the submarine was crushed in about 1/10 of a second. The reason I'm off on this tragic tangent is because standing in an atmospheric pressure that's 90 times what you'd find on Earth is the equivalent of scuba diving at an oceanic depth of roughly 900 meters, or getting chomped by my 2 imaginary puppies at the same time. Venus is also the most volcanic planet in our solar system, with an estimated 1,600 active volcanoes. If we combine this with the atmospheric composition and its proximity to the Sun, it gives us a planet that rains sulfuric acid and has an average surface temperature of 460 degrees. Which means if we wanted to make a lake on Venus as it stands today, we sure couldn't use water, but we could use lead. Venus also seems to be weirdly unlucky as far as human exploration is concerned. This isn't really a scientific measurement, but it is an interesting story. In 1981, the purpose-built spacecraft of the Venera 14 mission only survived less than an hour on its surface, which isn't actually the unlucky part. The designers estimated it would only last 32 minutes. But when the lens caps popped off the cameras that the probe used to take these pictures, one of the caps rolled right under the spot where a spring-loaded arm snapped down in an attempt to measure the surface's compressibility. Instead, they measured the compressibility of the lens cap. I can't even begin to calculate the odds of that particular slap in the face. I just know that it probably stung. Submarine crushing, lead melting, morale-destroying aspects of Venus aside, it is probably the best candidate for complete terraforming that we have in our solar system. We really could terraform Venus. It'll just take a lot of resources and a very, very long time. As much fun as it was to talk about why terraforming mostly won't work in the environmental horror circus that is our solar system, let's abandon practicality for a moment and go through the process with our best candidate, Venus, baking acidic murder air and all. To start, I should note that we're talking about slow, incremental changes here. These will take centuries, not decades. That said, even if humanity doesn't make any major technological discoveries in that period, we could still pull this off. Sure, fusion would make this easier. Fusion makes everything easier. But we can use sunlight for power right now, and Venus gets plenty of that. Without major biological or technological augmentation, Earth life needs the following to survive: air to breathe, water to drink, food to eat, comfortable temperatures, and shelter. So how do we get all of this on a planet that killed a purpose-built spacecraft in minutes? Well, there's actually one place on Venus that's quite comfortable for human life, at least in terms of the temperature. It also offers a hell of a view. At around 50 kilometers above the surface of Venus, the average temperature of the atmosphere is nearly Earth normal. So is the air pressure. Yes, there's still clouds of sulfuric acid floating around, but we can make suits and coatings acid won't eat through. Humans deal with sulfuric acid all the time. The amazing thing about this elevation on Venus is that due to the dense composition of the Venusian atmosphere, a blimp full of normal old Earth air will float quite handily. And the nice thing about filling a blimp full of breathable air instead of helium, like we do on Earth now, is that you don't need the little passenger compartment attached to the blimp. You can just walk around inside the blimp. The air you need to keep you flying is the same air you need to keep you breathing. Which means that instead of blimps, you could build a huge replica of Cloud City from The Empire Strikes Back. If you use a lightweight metal alloy or composite material for the structure, and then fill it with what we on Earth call air, if you've done your math correctly, it'll float just fine. Creating these little pockets of livable habitat on other planets is called para-terraforming. On the Moon and Mars, it would take the form of the classical domed cities, or just settlements under the surface. But on Venus, para-terraforming means soaring through the clouds. This sky colony would provide a convenient place to situate some of the infrastructure we'll need for the rest of the terraforming process. It would allow us to start mining the surface for materials, and it will let us begin the work of altering the atmosphere directly. We could even build a flying mass driver system. A mass driver is a kilometers-long launch tube that uses magnets to propel payloads off of the planet. And we could hold ours up with balloons. Terraforming Venus is going to require us to remove a lot of the stuff that's already there, while adding in a lot that's not. And a mass driver is an efficient system to toss out the things we don't want on the planet. And by a mass driver, I mean dozens at least. Most of what we'd want to get rid of is contained in Venus's atmosphere. The air on Venus is roughly 3.5% nitrogen, whereas Earth's air is almost 80% nitrogen. Even so, just like the 95% CO2 in Mars's atmosphere only amounts to a fraction of the amount contained in the 0.04% of Earth's air, because of its dense atmosphere, the nitrogen that composes that 3.5% of the air on Venus is actually 4 times the amount found in Earth's atmosphere total, even though, again, nitrogen makes up 80% of Earth's air. If that doesn't make any sense, screw words, here's a picture. So yeah, we'll need to get rid of some of that. But we won't just be shooting giant cans of nitrogen into the sun. The thing about nitrogen is that Earth plants need it to grow. If we have orbital habitats, a moon base, or really any other self-contained space infrastructure where people live in perpetuity, those facilities are going to need a supply of nitrogen. By the time we get a system set up to extract nitrogen from Venus, there's likely to be several destinations waiting to take it off our hands. Conversely, one thing Venus doesn't have enough of is hydrogen, at least not enough to make a new Earth, with rivers, lakes, and seas of water. We can pull hydrogen out of Venus's atmosphere. There's plenty of sulfuric acid floating around, and hydrogen is a part of that. From this source alone, we could probably get all the hydrogen we'll ever need for drinking water and any agricultural use we can think of. Probably with enough left over for quite a few heavy lift balloons, or the odd river or pond. But if we want oceans, we're gonna have to import hydrogen by the billions and billions of tons. Happily, hydrogen is pretty common. Actually, hydrogen is the most common element in our universe. But in our solar system, most of the hydrogen is tied up in, well, the sun, or the gas giants. Importing hydrogen on such a massive scale would pretty much solve all of our problems at once. Hydrogen will mix with the CO2 in the air to produce water and elemental carbon, basically graphite. If we truck in enough hydrogen, like 40 billion megatons, we would not only sequester the carbon and reduce the greenhouse effect, it would leave us with a world that's 80% covered by ocean. More than Earth. Without going too much into the how, let's just say that if we can get nitrogen off Venus, we can get hydrogen to Venus. We would just need a lot of it. But importing it could provide a partial solution to another big problem with Venus, the fact that its day is longer than its year. For a moment, let's ignore the multiple scientific publications that refer to Venus as hell. Pretend you're on Venus reading a book in a park, and it just got too dark for you to continue to read comfortably. Well, you could just hop on your bicycle, casually pedal to a park 30 minutes west of your origin point, and you'd regain enough daylight to finish your chapter. Or 2. This is because the day-night terminator on Venus moves about as fast as a human walks, roughly 6 kilometers an hour. A day on Venus, one rotation on its axis, lasts 243 Earth days, while its year, the time it takes to travel around the sun, lasts 225 Earth days. The extremely long day-night cycle on Venus means you get about 115 Earth days of light, followed by about 115 Earth days of dark, with like a week each for dawn and dusk, respectively. That long night would be a real bummer for any plants that like photosynthesis, or people who enjoy sanity. But our plans to import a bunch of hydrogen would actually help us shorten Venus's year-long day. The thing is, we don't need to unpack the hydrogen when it gets to Venus. You can just put it anywhere, which includes ramming it into the planet at a high enough velocity that it makes the planet rotate a bit faster. A huge asteroid impact is one theory behind why Venus has such a long day in the first place. And these kinds of impacts work the same for icy comets, giant asteroids, or big canisters of water and hydrogen. But we probably won't completely change Venus's night from 243 days down to 24 hours. The amount of energy it would take to do that is catastrophic. We'd be adding a ton of thermal energy to an already hot planet, and using anything other than fairly small objects would risk blowing chunks of the planet off into space. Even so, if we need several billion megatons of hydrogen shipped in, we will be spreading out these impacts over a few hundred years anyway. In the end, if we decide we don't want to surrender 80% of the surface of the planet to ocean, and we decide to only bring in enough hydrogen to add the odd sea here and there, not cover the entire planet, we could still shave a few hours to weeks off that long Venusian night. But the reason I mentioned such a giant amount of hydrogen is because that's how much it would take to sequester all the carbon in the atmosphere. If we don't bring in that much, it does bring back the biggest problem with Venus, all that carbon in the atmosphere. If you elect to not bring in hydrogen for hundreds and hundreds of years, you'd literally have to block out the sun or something to combat the greenhouse effect. So how do we fix that? Well, one way would be to block out the sun. In part 1, I mentioned that you could cool down a planet by putting a thick layer of crap into the atmosphere. This would block sunlight from ever depositing energy onto a planet's surface in the first place. The asteroid impact that I mentioned in episode 1 isn't the only way to create said layer of crap. As those of you who live on the west coast of the United States can attest, an opaque atmosphere will chill things down in a hurry, no matter how you get it. And I have my own recent example to prove it. A few days after I released that last video, it was supposed to hit 38 degrees in my small Oregon city. It didn't quite get there though. Actually, it missed the mark by about 17 degrees. This wasn't some colossal screw-up on the part of my local meteorologists though. Not really. I'm sure their forecasts were accurate, except for the fact that they didn't account for the giant layer of smoke hanging over the state. It was a strange moment to think that maybe I'd spent so long editing a video about Mars that I was now hallucinating its surface when I looked outside. Thankfully, the ash that was literally falling into my living room let me know that I wasn't going crazy. I just had ash falling into my living room. This series is about those changes we can make to other planets to make them more like Earth. Terraforming. And a viewer from last episode suggested we call the changes that we're making to Earth's climate Venus forming. They have a point. The wildfires that we've seen over the last few years as summer ping-pongs its way back and forth between Earth's hemispheres are a terrible manifestation of the greenhouse effect that we've created on our own planet, making it a bit more like Venus all the time. The intense cooling effect of all the smoke released by these recent fires let a lot of us experience just how drastic a change in temperature can be affected by blocking out solar energy. I would have rather not had this handy illustration, but it was timely. As effective as it is, using an atmosphere as a solar shield isn't really ideal. Atmospheres are turbulent things, which cover an entire planet. What you do to one part of it will generally end up affecting the whole. On Venus, making the atmosphere thicker is kind of the last thing we'd want to do. And even if we did, how would we do it? If Venus had forests to burn, they're long gone. And a giant asteroid impact kind of creates its own problems. But an atmosphere isn't the only place that we can put our solar shield. If our goal is to keep sunlight from hitting the surface of a planet, then we really have anywhere between the planet and the sun to work with, including all this space. There are these things called Lagrange points. They're the points where the ebb and flow of gravity is equalized between two large co-orbiting bodies in our solar system. It works the same whether we're talking about the Earth orbiting the Sun or the Moon orbiting the Earth. Practically speaking, this means that if you stick something in a planet's Lagrange point, it'll mostly stay there, with only minor tweaking. There are always 5 Lagrange points, and they're always numbered, L1 through L5. The L1 point is always the one directly between the two masses. And because physics works the same way everywhere, Venus is no exception. It has 5 Lagrange points, just like everywhere else. Its L1 point lies directly between it and the Sun, which makes this L1 point the perfect spot to fill up with hundreds of solar shades. The stuff we're sticking here could be mirrors, solar panels, a bunch of asteroids, doesn't really matter. There is an optimal way to do this, which I'll get to in a minute, but as long as sunlight can't get through whatever we put there, we're good to go. And this solar shield is probably the most important tool that we have for terraforming Venus. By reducing the amount of solar energy that gets to Venus's atmosphere, we'll rapidly lower the temperature of the entire planet. Because of the intense pressures in the atmosphere, once we cool things off enough, all that CO2 in the air will begin to condense into a liquid. We'd get lakes of liquid CO2 on the surface, at first anyway. As more CO2 rains out of the atmosphere, the pressure and the temperature would continue to drop. At some point, all that CO2 rain will turn to snow, and then those lakes will turn into huge deposits of frozen carbon dioxide. Venus will be covered in a thick layer of dry ice. At this point, we have a few choices. We can either export carbon to the rest of the solar system to use as a building material until we dig down to the rocky surface of the planet, or we can ship in soil and dirt and just cover the layers of dry ice with a few meters of dirt and rock as needed. Terraforming Venus completely will likely use a combination of all the methods discussed thus far, shipping out nitrogen, shipping in hydrogen, and using our solar shield to regulate the temperature until we get a balanced atmosphere of Earth temperature air, at a pressure that won't make your bones implode. Getting to this point would be a huge milestone. But there's a few now whats that I need to mention. For one, once we get to the point of reducing Venus's air pressure, those awesome floating cities that I mentioned will look exactly like less awesome regular cities if you crash them into the ground from a few kilometers up. That's exactly what they do, without the ridiculously thick atmosphere to support them. So at a certain point in the future, we'll either have to decide that those para-terraformed cities are only a beautiful step in our march towards building a second Earth, or we'll get to a point where the floating infrastructure of Venus is so extensive that we'll just stop there and keep doing that. Living in enclosed flying habitats among the clouds of Venus is a perfectly valid endpoint for the human colonization of the planet. The other thing that happens once we reduce the thickness of the air is that we again have to worry about solar storms blasting away our carefully crafted atmosphere. In part 1, I was pretty dismissive of a NASA proposal to give Mars an artificial magnetic field. But we could do the same thing on Venus. And this time it would be worth the effort. The combination of mirrors and solar panels that we put in Venus's L1 point to block and reflect solar energy could use some of this energy to power the artificial magnetic field. Conveniently, whatever light we didn't need to power the field, we could reflect off huge arrays of mirrors which would orbit Venus. With enough of these mirrors, we could create the appearance of another, dimmer sun on the night side of Venus, which would break up that marathon day-night cycle into chunks manageable for Earth life. Now that we're probably a century or two into this process, we can finally start to populate the biosphere of our new Earth. I realize that this is a huge undertaking, but the difficulty is in the scale, not the theory. We know how to do all this. We have the tech to do it right now. It's just a question of time and effort. This huge effort is why I was more dismissive of the idea to build an artificial magnetic field around Mars. For one, we'd have to import far more nitrogen to make Mars habitable than we would hydrogen to give Venus an ocean of liquid water. And even if we did all this on Mars, best case, we'd have an environment with less than half the gravity of Earth and only a fraction of the available solar power to boot. With Venus, we'd end up with a planet much like Earth. Similar temperatures, abundant solar energy, gravity that's different enough to be interesting, but not enough to cause long-term health problems, a travel time roughly half of that to Mars, and much, much more surface area than Mars offers. What we would have is the closest thing to a second Earth as is possible in this solar system. Every time that humans exert our will on the universe, there's a price to pay. Sometimes that price is translatable into a currency, sometimes it isn't. In my video exploring how much money it would take to fund an asteroid mining company, the numbers involved were gigantic, but still small enough to put into a meaningful context. For a project as large as turning Venus into a new Earth, we're talking about an economic scale several orders of magnitude beyond the current global exchange. In terms of expended energy, labor, logistics, materials, planning, etc., I really don't have a way to calculate the price tag in a dollar amount that would make any sense at all. Even if I could, doing so would make about as much sense as this one time a reporter asked Stephen Hawking how many dimensions there are in space-time. What the hell is that reporter, or you or I for that matter, gonna do with that answer? Check his math? An answer is meaningless without context. He said 11, by the way. I don't know exactly how much money or energy or time it will take to turn Venus into a new Earth, but I do know one concrete thing that we'll have to sacrifice to make that happen. Venus. Completely converting Venus into a new Earth means no more floating cities, no sky surfing using just some strap-on wings, a backpack of air, and an acid-proof suit, no watching a sunset from the balcony of a flying house. A sunset which involves a sun that looks 40% larger than it does on Earth, slowly setting behind billowing clouds of sulfuric acid over the span of several days. Also, no scale-accurate Disneyland Bespin theme park. I'm not saying that having a second Earth wouldn't be worth losing all that, and more. I'm just saying we can't have both. Luckily, undoing the greenhouse effect on Venus will be a slow enough process that we'll have time to fully understand our options, before we're so far along that we can't turn back. Plus, I bet we'll have a lot more experience dealing with this whole greenhouse effect thing before you can buy a ticket to a city in the clouds. Call it a hunch. So, would you rather have a new Earth or live in a flying city? Acid clouds and all. Let me know in the comments. I'm genuinely curious how you all feel about this one. Also, at the moment, going on over at the channel's Patreon page, we have a poll to pick the next episode. Any contribution at all lets you vote. The link is here and in the video description. And of course, you can always suggest a future topic in the comments section below. If you're able and compelled to support the channel on Patreon, like these lovely people did, I don't think I'll ever be able to effectively articulate my thanks and appreciation, but I will continue to try. Please leave a comment, hit the like button, subscribe if you think I've earned it. Thank you so much for watching, and I'll see you next time.